Last week, we started our discussion on the derivative, and all we did was define the derivative. So just recall how we defined the derivative. Well, recall the derivative is a function which gives us the slopes of tangent lines. And to find the slope of that tangent line, we used a limit of the slopes of secant lines. A secant line, we had 2 points, and then in the limit, we let that secant line approach a tangent line. So given an x, we have a function. The derivative will give us the slope of this line, and that x can be any value. Find it as the limit as another quantity h went to 0. We technically defined it in 2 ways. We will use, for the most part, the second way. Slope of the secant line, and then we let that approach the tangent. Here we have the definition. So today we're going to use the definition, and then we're going to look at some algebraic rules that the derivative satisfies. Any questions about that? Okay, what's the first example? X squared plus 4. So on exam 2, which is 2 Mondays from now, covering this week and next week, there will be a question which says, find the derivative using the definition. So for the next maybe half hour, all we're going to have is the definition. If it says to use the definition, you have to use the definition. If it says, well, if it doesn't say to use the definition, you can use the rules we covered later today. So example. For these examples, I won't say use the definition because that's technically all we have. Homework, worksheets, exams, it will say to use the definition. Find f when I want to use the definition. Find f prime of x. So I need to give you a function. We're going to find the derivative of f prime of x. X squared plus 4. We have that definition. So if we want f prime of x, we use this definition, given this function. That definition says the derivative is the limit h approaches 0, f of x plus h. What's f of x plus h? Well, take our function f and substitute x plus h. Replace all x's with x plus h. We have x plus h squared, and then that 4. Any questions about finding f of x plus h? Okay. Minus f of x, so we subtract f of x. Subtract all of f of x. If you don't subtract all of f of x, the algebra won't work. Or the eventual algebra won't work. And then divide by h. So all we've done here so far is use the definition to get a limit which we have to compute. Any questions about getting to this line? Okay. I don't think that's going to fit over here. Yeah, I'll have to go down to the next line. So how can we compute this limit? Well, it's a limit. We can hope substitution h equals 0 works, but if you let h equal 0, you're going to get a 0 over 0. Every time in this first step, you'll get a 0 over 0 because it's set up to give you a 0 over 0. But what we can do is some algebra. Here we can square x plus h. X plus h squared. X squared plus 2xh plus h squared. And then we'll just write the rest of it as positive 4. I'll also distribute that negative. So plus 4, negative that. Distribute the negative there, gives you a negative 4. And it's still all divided by h. Now, to simplify this, well, again, in this step, we haven't done any canceling, so we should still expect a 0 over 0, and we do get a 0 over 0 with substitution. But there is a little more simplification we can do because, where's the color? Because, notice, we have a positive 4 and a negative 4. They add to 0. We also have a positive x squared and a negative x squared. And those also add to 0. So a couple terms added to 0. What happens when we, rewrite this without those zeros written in? It's still a limit. We haven't taken a limit yet. But all we have left are 2xh. We have h squared. And it's still divided by h. Any questions about getting to here? Okay, we still have not taken the limit, and we still can't substitute h equals 0, because again, you get 0 over 0. But we can notice here, all of these terms have an h. The 2x has an, or the 2xh has an h, the h squared has an h, the denominator has an h. So we can cancel an h from each term. Another way of seeing that is factor out an h from the bottom and then cancel that with that top h. I'm gonna have to go to the other side of the board here because, but we can cancel an h from each term. What happens? We still have not taken a limit. Cancel an h from 2xh, you have just 2x. Cancel an h from h squared, have h. Cancel an h from the denominator, that turns into a 1, so I'm not going to write divided by 1. And now we can take this limit by substituting h equals 0. Let h equals 0, you get 2x. Any questions about this first example using the definition of the derivative? Okay, let's just do one consequence of this first example. We'll call it another example. Find the slope of the line. Which line? I'll have to give you a line. Notice the function from the previous example, x squared plus 4. We can graph using graph transformations. Take x squared, standard parabola for 0, 0. Lift it up 4. Where am I going to write this? I'll write it here. So here we have f of x. I should write that higher. Take x squared, lift it up 4. So here we have f of x squared plus 4. It goes through 0, 4. I'm not going to write that because it will probably get in the way. But find the slope of the line. I don't see a line, other than those, I guess. But find the derivative we can use to find slopes of tangent lines. So we have a curve here. Let's throw a tangent line somewhere. Let's make it a different color in the hopes that it's a little more clear. Find the slope of the line. Maybe I should say bright line. Here we have a tangent line, and it's at x value, let's say, too many 4s. Let's say x equals 3. So we have this curve, we have a tangent line. Find the slope. Well, the slope of this line is given by the derivative evaluated at 3. By the definition, the derivative is defined to give us the slope of this tangent line for any x value. I just said x equals 3 here because it was close to 3. So the slope of that line is f prime at 3. And what's f prime at 3? Well, f prime at any x is 2x, so f prime at 3 is 2 times 3. So that line has slope 6. Any questions about that second example? Well, let's extend that slightly further. We have the slope of the line. Let's find an equation for the line. And right here is going to be the first example we do where it becomes much more clear why in calculus the point slope form is more convenient. Find an equation for the red line. That says line. Find an equation for the red line. Well, we need a point. We need a slope. Well, the slope we already found from the previous example. 6, maybe I'll just write an arrow, previous. Maybe I'll just say m or f prime. I'll say f prime. Find the equation for the red line. That's the tangent line when x equals 3. F prime at 3 equals 6, and then I'll just say previous example, since we did that. We need a point and a slope. So here's the slope. Any questions about slope? Okay, now we need a point on the line. Notice in this curve that we have a point on the line. There is a point on the line when x equals 3. Notice also that that point, since it's tangent to the curve, is on the curve f of x. So if we want that point, which we do, that's the most convenient point to find here. Actually, it's the only point we can find on this line. It's on the line, but it's also on the curve, which means we can use the curve f of x to figure out the y value. When x equals 3, f of x is 9 plus 4, so 13, and maybe I'll draw an arrow here, f of 3 equals 9 plus 4 equals 13. So we have a point and the slope. An equation for the line would then be y minus the y value equals the slope times x minus the x value. Of course, if you did want slope intercept, you get 6x minus 18 plus 13, so 6x minus 5. But I'm never going to ask you to simplify.
Hey, can you explain how you got 13, please?
Yes. So this point is on the curve f of x. It's also on the line. So to find the y value, we can use our original function. F of x equals, because that is the only spot I'm certain, f of x equals x squared plus 4. So let x equal 3, you get 3 squared plus 4, 9 plus 4 gives you that y value.
Okay, thank you.
So do notice that in finding an equation for the tangent line, what we really need to do is interpret the function at the value and the derivative at the value. And then we just have to be sure we're organizing it. Any other questions about this one? let's do 2 more examples using the definition. Yeah, and then we'll go to the derivative. Which one do I want? X cubed minus 4x. And again, these are, since we have right now for the next, I guess maybe about 20 minutes, we have only the definition. So find f prime for the function x cubed minus 4x. Well, again, first thing we do is substitute into definition. Limit h goes to 0, f of x plus h. I'm going to have to erase that board over there. Maybe that's right. F of x plus h, replace all x's with x plus h. So here we have f of x plus h minus f of x minus f of x all over h. So now we're going to need to simplify this a little so that we can take the limit. How can we simplify this? Where do I want to simplify it? I'm going to simplify it. There will be a large quantity of side work. How can we simplify this? Well, for that second piece, we can distribute the -4. For this piece, we can distribute the negative. But what about the cube? Well, you could write out the cube. Write out x plus h times x plus h, then multiply again. You could have that cube formula memorized. I think that cube formula has a lot to memorize. Another way we can expand binomials raised to positive numbers is by using a combinatorial tool called Pascal's triangle. Combinatorial in math. Combinatorics is the study of counting in math, which may sound simple, but it becomes very complicated very quickly. So let's discuss how we can use this thing called Pascal's triangle to simplify that cube. On your worksheet, you have this to the 5th, and you could multiply it out. It would probably take significantly less time to use what we're about to do. Now, how do we form this triangle? Well, it's going to be a triangular array of numbers, where in the first row, well, maybe I'll say the top row up here, we have a 1. In the next row, we have 2 1s. And they start forming a triangle, an equilateral triangle, with that top row 1 as the upper point. So we start with these 1s, and then we fill in the rest of the triangle as follows. The next row, start with a 1, end with a 1. The first row will have 1 element. The top row, I'll explain why I don't want to say first in a moment. The top row has 1 element. The next row has 2 elements. This one's gonna have 3, the next one 4, and so on. Start and end with a 1, and then this number between the ones will be given by the 2 numbers above it added together. In this case, 1 plus 1 gives us a 2. Maybe I'll put a little more space here. 1, 1, 1, 1, 1, and then the middle number here is given by that 1 plus that 1. Now, the next row is where the pattern really starts to take more form than just in the second row. So, or in that row. 1 element, 2 elements, 3 elements, the next one with 4. It's again going to start and end with a 1, but we need 2 more elements. And how do we find them? Well, 2 more elements. This one is going to be the 2 numbers above it, 1 to the right, 1 to the left, added together. 1 plus 2, 3. The next one is going to be the same thing. Well, the same thing in the sense of the 2 numbers above it added together. In this case, 2 plus 1, another 3. And then let's form the next row, maybe the next 2 rows. I think I have space for that. 4 elements here. The next one is going to have 5. It's going to continue to form triangularly like this. We need 5 elements here. We have the starting one and the ending one. The 3 in the middle are given by this number plus this number, 1 plus 3, 4. The 2 numbers above it added together, 3 plus 3, 6. 2 numbers above this one added together, 3 plus 1 is 4. And let's form one more. Well, any questions about forming, well, any of these numbers? Start with 3 ones. Any questions about forming this? Okay, let's do one more row. This row down here has 5 numbers, so the next one is going to have 6. Start and end with a 1. The middle 4 are 1 plus 4, 5. 4 plus 6, 10. 6 plus 4, 10. 4 plus 1, 5. And then you can keep forming rows as you need. In the worksheet example with x to the 5th, if you use this triangle, that is the row you use. So any questions about forming this? Now, how can we use it? Well, this triangular array of numbers has many, many applications and many, many branches of math. One of those applications is that we can use it to expand something like x plus h to the 3rd. 2 things added together, raised to a number. Or subtracted, but we won't see that in this class. So how can we use it? Well, where do I have room to use it? I'll be able to fit it up there. How can we use it? Well, x plus h to the 3rd. Look at the exponent. We go to the row where that exponent is the second number. In that case, 3. The second number here is 3. We take this row, 1, 3, 3, 1. This row is going to give us the coefficients. 1, 3, 3, 1. I'm just going to move the triangle over a little, actually. Stop it there because that's all we need for this example. Go to the row where the exponent is the second number. 3 is the second number in that row. This gives us the coefficients. Now we count. X plus h cubed. What does this equal? Well, 1, 3, 3, 1 give the coefficients. So I'm going to write 1. Gonna write 3, gonna write 3, gonna write 1, gonna write them with different spacing, so it looks better. 3. No. First one was 3, 3, 1. And in this quantity, all of these are positive. So these are all going to be eventually be added together. So we can write them as positive 3, positive 3, positive 1. Now, what do we do from here? Well, we have in this quantity, two quantity in this formula, we have two quantities, x and h. And what we do is we put 3 total letters on each of these numbers in a certain way. In what certain way? Well, let's start with x, our first one. X. We're going to put 3 x's on this first coefficient. Put 3 x's there, which we can write as x cubed. Then we're going to put 2 x's here. X squared. We're going to put 1 x here, x to the 1, and we're going to put 0 x's here, x to the 0. And then we do the same thing with our second piece, with our h, except we do it in reverse order. So our second thing is h. We'll put 0 h's there, 1 h there, 2 h's there, 3 h's there. And notice each of these 4 numbers now has exactly 3 letters on it. 3 x's, no h's, 2 and 1, and so on. Now in math, it's common to not write 1s if you don't really need them. H to the 0 is 1. H to the 1 we usually just write as h, and similarly for the x's. So 1 and h to the 0 are both 1. X cubed times 1 is x cubed, and so on. But that simplifies to this quantity, which again, you could have gotten through direct multiplication. You could have gotten if you had a formula memorized. But you know, Pascal's triangle, it's kind of it's a very useful tool in math, but it's, you know, it's nice to work through something like this because it helps keep you organized when you're counting things. 3 of those, 2 of those, 1 of those, 0 of those, and so on. Now, on your worksheet, you have one with x to the 5th, and I would recommend practicing it with this, with the 5th row, one with 5. Now, question remains, would this be tested where you have to use Pascal's triangle? And the answer is no. Meaning, if you had a definition with a polynomial, the largest exponent I've ever tested was 2, I think. And with 2, you know, using Pascal's triangle might be a little overkill. But you know, especially those of you who are taking math more than just Calc 1, it's definitely a good idea to practice using that, because it does, you know, especially for the one with like x to the 5th, it does make it a little simpler. Any questions about where that came from? Okay, now why did we do all of that? Well, we did all of that so that we could solve this limit. X plus h cubed is now given by that quantity on the bottom. X cubed plus 3x squared h plus 3xh squared plus h cubed. And next I'll distribute the -4, distribute the -1, and write all this. So -4x, -4h, negative x cubed, negative 4x, which makes positive 4x. This is all over h. Well, how can we solve this? Well, we can't substitute yet, we get 0 over 0, but we can observe there's much canceling. X cubed, negative x cubed, cancel. Positive 4x, negative 4x, cancel. And what are we left with? Left the limit as h goes to 0 of what? 3xh or 3x squared h. 3xh squared. H cubed is still there. Negative 4h still there. And the h in the denominator also still there. Now we've canceled everything. Now that we've canceled everything that cancels, we're left with terms, all of which have an h in them. So we can, again, as in the previous example, cancel an h from each piece. Cancel an h from 3x squared h, 3x squared. Cancel an h from 3xh squared, 3xh. Cancel an h from h cubed, h squared. Cancel an h from negative 4h, negative 4, all over h, which cancels. Cancel an h from h, you're left with 1. Right divided by 1. And now we can let h go to 0. Let h go to 0. 3x squared remains 3x squared. 3xh goes to 0. H squared goes to 0. Negative 4. 4. And we get 3x squared minus 4. Any questions about this example? Did a bit of a sidetrack to simplify the cube. The details in that I will reference back to when we talk about a result in about maybe 15 minutes. So any questions about that? Let's do one consequence of this. Find all x values at which f of x equals x cubed minus 4x as a horizontal tangent. Find all x values at which that has a horizontal tangent. Okay, what does a horizontal tangent look like? Well, let's draw one and see what it looks like. Well, a horizontal tangent line is a tangent line which is horizontal. So what could that look like? Well, if we have a general curve like this, a horizontal tangent could occur at a point like that where the tangent line is horizontal. A tangent line, over here isn't horizontal, it's slanted. But a tangent line down at the bottom of this piece is also horizontal. So we notice here the slope, maybe I'll say it in fewer words. We'll notice here f prime, the slope of the horizontal tangent line is 0. So in particular, the slopes of these two lines is 0. Slope of a tangent line we can find using the derivative. So we need to find, well, for both of these lines, the derivative is 0 because the slope of the tangent line is 0. So f prime equals 0 for, well, I'll just say f prime equals 0 here and here at those 2 points. Let's do it. F prime equals 0 at both of those x values. So if we want horizontal tangent lines, we need where f prime equals 0. So here we set f prime. Sometimes I don't write of x if I think it gets in the way. Right here, I think it would have kind of gotten in the way. I think that's okay. So we're looking to find horizontal tangent lines. We're looking for where the derivative is 0. Well, in the previous example, we found that f prime of x is 3x squared minus 4. Solve this for x. Add 4, divide by 3. X squared equals 4/3. Solve for x. Square root of 4 is 2. Square root of 3. Square root of 3. And here we need all x values where x squared is 4/3. So we do need the positive and negative. And you don't have to get rid of that square root. Any questions about that one? Okay, let's do one more example where we use the definition before we cover some algebraic results. Find f prime of x here. Root x, find the derivative of x. Well, again, definition. Limit as h goes to 0, f of x plus h minus f of x over h. Very important quantity in math. Now this limit is very important for a very specific reason in calculus. The next couple weeks, we're going to be talking exclusively about the derivative. And for the most part, after this example, we're not going to really mention limits that much. But the derivative, which we are going to talk about for the next few weeks, relates the definition shows very nicely how what we covered first, limits, relates to what we do afterwards. It is very important. It may seem like on exam 2, when a definition of derivative question is asked and on final exam, it may seem like you're doing a lot of work for little information, but it actually does tell you a lot of information about calculus because it relates the first 2 parts of the semester. We have this definition. In the first 2 examples, I didn't actually write this definition at work, but here I guess I will since I did. F of x plus h, replace x with x plus h. I have to write this on the next line. F of x plus h is root x plus h minus f of x minus root x all over h. How can we take this limit? Well, we can't substitute h equals 0 because we get 0 over 0. But we have seen ways we can remove square roots. And we can do that here. We can multiply by a convenient 1, which will force these square roots to go away using the difference of squares. Multiply by x plus h in a square root plus square root of x. If you do that to the numerator, the square roots will go away. If you do that to the numerator, you also have to do that to the denominator so that it doesn't turn into a new problem. So what does this equal? Well, limit h to 0. As we saw in some of the limit examples, like 1b on the test, distributing the denominator in these cases would not help us because we would eventually have to undistribute them to cancel what we need. So we'll leave this denominator as h times that quantity over there. Leave that undistributed. And what happens when we distribute the numerator? Well, first thing squared, x plus h, minus second thing squared, minus x. So from the difference of squares observation, the numerator is just the first thing squared minus the second thing squared. Any questions about that first step in simplification? I guess it's the second step. Okay, now what can we do? Well, we can't substitute h equals 0, but we can notice that x and negative x add to 0, so they cancel on the top. X and negative x add to 0. We're left with h on top, which will cancel with that h in the bottom. I'm going to do those two steps in one step. X minus x is 0, and then we have just h on top, which will cancel with that h on the bottom, leaving us with 1 over x plus h square root plus square root x. And now we can let h equal 0 and simplify. Let h equal 0, 1 over root x plus root x, 1 over 2 root x. Any questions about this one? So in this one, we had to use one of our limit simplification tricks. I guess you can call that a trick, kind of. You know, multiplied by a fancy 1. Okay, so we've seen a few examples where we use the definition. I forgot to mention one thing I was going to mention back on Pascal's triangle. It's a quick mention. I mentioned that I don't like calling the first row. Well, in here, because it has a 3, it's common to call that the third row, even though it's the fourth row. Now, one way of getting around that is by calling the first row the 0th row, because that gives you x plus h to 0. And that's making the second row what we call first, because of the 1. The third row what we call a second. So in math, there are times where it's convenient to start counting at 0. There are times where it's convenient to start counting at 1. So for completeness, this is why, if I say the third row, I actually mean the fourth one down in that context. But you don't have to worry too much about that. And just follow the exponents. Okay. So we've seen a few examples where we use the definition. This definition of the derivative allows us, we can use the definition to find general derivatives. Meaning in those first examples, we looked at some specific derivatives. Well, we can generalize some functions. And we're going to call these the algebraic derivative rules. Maybe I shouldn't call them out algebraic because we're going to have trig. So let's just call them derivative laws. For about an hour right now, we're going to discuss these derivative laws and use them. These will be posted on Canvas. Again, I have to scan that. They're going to be 3 pages with 16 rules. And it's very, very important to practice these. It's especially important to practice them before tomorrow. So on our worksheet, I'll mention this later as well today. before tomorrow's class, it's very, very important to practice something like the 10 parts of problem 3, which is why I put so many parts there. Problem 3 in the worksheet. Because tomorrow we're going to build on these derivative laws. Now, what are the derivative laws? Well, should I list them or discuss them and then list them? This is going to turn into, I am going to post this as a PDF, but if you are taking notes, this will, I'm going to write it as a table. So the derivative, to find, well, the derivative is a function. It's a new function given an original function. So here we're going to have a list of 16 general functions. And their 16 corresponding derivatives. So this will turn into 16 rules. I'm not going to write all 16 right now, because I'm going to write some and then discuss them. We'll prove a couple of these and we'll use all of them. Well, there's one function. The constant function c. F of x equals c. So like f of x equals 1, f of x equals 12, f of x equals -5, f of x equals pi. Those are all constant functions. What is the derivative of a constant function? So again, there are going to be 16 rules in that list. I'll prove a few of them. I don't know, maybe 4, maybe 3, I don't know. Proof of the constant. Well, let's do this one first. And these proofs are going to use the definition. So what happens in general to the constant function when we take the derivative? Well, the derivative is the limit as h goes to 0 plus h minus f of x all over h. Sometimes my h's look like l's. These are all h's. When you have to write h 50 times, sometimes you don't make them look entirely like h's. But that is the standard letter here. So what is the derivative here? Limit h goes to 0. What's f of x plus h? Well, the constant function, replace all x's with x plus h, you're left with c. Minus f of x, replace all x's with x, you're left with c. All over h. How can we compute this limit? Well, let h equal 0, you get 0 over 0, but notice the numerator is always 0. This fraction always simplifies to 0 for h approaching 0, and then the limit as h approaches 0 of 0 is 0. Right there, we showed the derivative of any constant function is 0. And we showed that with that observation. We could also just observe, well, any questions about that computation over that? An alternative way of proving that over there is just by looking at a constant function, horizontal line, and observing that the slopes of any tangent line, the line tangent to that is a horizontal line. It's the same line, but the slope of a horizontal line is always 0. So for this first rule, there is a geometric observation to make as well. There's one derivative rule called the derivative of a constant, well, the constant rule. X to the n. N is a number. Technically, to prove it for any number, you need a future result, but for this, I'll just say this works for every number. X to the n. X to some number, this is a power function. maybe I'll just say in parentheses. And we're going to call these rules certain things at some points throughout the semester. First one is the constant rule. The next one, x to the n, where n is a number, x is our variable. A power function, we're going to call this the power rule for taking a derivative. What is the derivative? Well, I'll tell you that the derivative is that exponent n times x to the n minus 1. So given nx to the n, we can find its derivative, nx to the n minus 1. I'm not going to prove this one, but you can, in the example we did, x cubed minus 4x. Notice in the expansion for x cubed and taking the limit, most of those terms went away, except the 3x squared part. In general, most of those terms will go away. And in the example on the worksheet, problem on the worksheet, problem 2 with x to the 5th, you can also see how a lot of terms will cancel. But I won't show you a proof of that, but I will just illustrate it here. Illustrating power rule. F of x equals x cubed. That's a power function. Call this the third rule. Oh, shouldn't. Okay. We have here a power function, x to a number, a power function. We can use that rule to find the derivative. With n equal to 3. What happens when n equals 3? Well, we get 3x to the 3 minus 1. So what's that? Well, that's 3x to the 3 minus 1. And what's 3 minus 1? 2. So the derivative of 3x squared, or sorry, the derivative of x cubed is 3x squared. And in that example with the definition, if you go through the details, you can see where the 3x squared pops up, because that was part of our answer. Now let's do one more. Let's call that A. Let's call this B. F of x equals x to the 37. 37 is a nice number. So you could find this derivative if you want using the definition. Going down to the 37th row of Pascal's triangle, expanding everything, noticing that 36 things cancel out. Or if you don't want to use the definition and you're not told to use the definition, we can use the power rule. Over there, the derivative is nx to the n minus 1. Here, n equals 37. So 37x to the 37 minus 1, which is 36. And that also works for negative numbers. We'll see a couple examples of that as we go along. Any questions about, well, the second rule and illustrating the second rule? It's definitely worth observing in the second worksheet problem with the x to the 5th. It's worth comparing the canceling step in the x to the 5th problem to the canceling step in the definition problem with x to the 3rd. Worth observing. In this chart, C is going to be a constant, X is our variable, F and G are going to be functions. So here we have C times F, derivative of a constant times a function. Well, the derivative of that, back when we did limits, one of the conveniences about limits was that if we had a bunch of x's with a number next to them, we could jump past that number and deal with the x's. meaning in a computation, we can just carry the number through and worry about the x's. Here, we can do the same thing. If we have a constant times something with a bunch of x's in it, and we want the derivative, we can carry that constant through and then multiply by the derivative of that quantity with all of the x's. Now this is another constant rule. I'm not going to call it anything. A proof of that rule follows because, in both pieces of the numerator you can factor out a constant. I won't go over a proof, but we'll illustrate that rule as we do some examples, and we'll see where that shows up. I won't do anything with it right now, but it's a very important rule because it allows you to see less than is written in some sense. Next, when we were doing limits, we had rules for sums and differences of functions. So we have f plus or minus g. With limits, we were able to do those limits one piece at a time. And we can do the same thing with derivatives. We can take the derivative one piece at a time. Sum difference rule. Do I want to prove this or do I want to illustrate it? Let's see, I'm going to prove either this one or the product rule, which is next. Which one is less uninteresting? Product rule proof is kind of a pain. Let's prove this one. No, let's prove the product rule one. Let's just illustrate this one. Let's illustrate the sum and difference rule with an example. Find f prime of x, or let's say x to the fifth plus 2. I think that's what's on the worksheet. X to the fifth plus 2. Well, if we want the derivative here, we have two things added together. Now let's make it a little more interesting, sorry. Yeah, you can leave that too. Sorry if you erased it. 2x squared plus 1. So this is actually illustrating rules 3 and 4 in that list. Okay. We have three things here added together. They could also be negatives. We'll deal with negatives in a moment. But the fourth rule says we can take the derivative one piece at a time. Meaning we can first take the derivative there, then take the derivative there, then take the derivative there, and then add all the answers together. So first, we'll deal with x to the fifth. X to the fifth is a power function. We can use rule 2 to get 5x to the 5 minus 1. So 5x to the 4th. Any questions about, maybe I'll draw an arrow here to make it clear that we're just doing this one piece at a time for this. Any questions about that first piece? Okay, how about the next piece? Well, we have 2x squared, but first I'd like you to observe 2x squared has a 2 and it has an x squared. So it really has two things going on, a constant and then a bunch of x's. Well, third rule says carry the constant down and then deal with the x's. So let's carry the constant down. It's a positive 2. And then deal with the x's. If it were a negative 2x squared, you can carry a negative 2 down. So carry this 2 down and then deal with the x's. X squared, the derivative of x squared, that's another power function. N equal 2. with n equal 2 in the power rule over there. You get 2x to the 1, which you can just write as 2x. So for that second piece, we're actually using the third and second rules in that list. And the third piece, we have a 1, derivative of a constant is 0, so plus a 0. And now we'll just rewrite it so it looks a little better. 5x to the 4th is 5x to the 4th. 2 and 2x make 4x. 0. Write 0 when you have 0. Any questions about this example? So this one actually illustrated all 4 of the rules. Now I'll just say it out loud for this example. If this were a negative, that's the element 2x squared, that would become a negative, which would make that last answer a negative 4x. So any questions about those first 4 rules? Okay. Maybe I shouldn't erase that. I'm going to continue the chart over here. Do the work over there. We have 4 rules so far. 5th rule. Well, with limits, we had some similar rules. We had that sum and difference rule. We had a constant rule. We had a product rule for limits. What happens with a product of functions of f times a g? Well, I will tell you, with limits, you can do it one piece at a time. With derivatives, you can't. And I will prove this rule in the proof. Well, the details are in the proof. But with derivative of a product, you can't just do the derivative of the first thing times the derivative of the second thing. What you have to do is follow this structure. The derivative of a product will have 2 pieces. Derivative of f times g, f prime times g, plus f times g prime. So it's the derivative of one of them times the other, plus the derivative of the other times, the derivative of one of them times the other, plus the one you didn't take that you took the derivative of, times derivative of the other. So we have the derivative of both pieces showing up, but they get multiplied by the other function left alone. We call this the product rule. Let's prove this and let's illustrate it. Proof of this has a, well, it has details, let's just say. So in doing a couple limits, we've multiplied by 1, which doesn't change anything if you multiply by 1. Here, we're going to add 0, which also doesn't change anything. Well, it changes what it looks like, but it doesn't change the function. Let's do proof of the product rule. Is this going to fit here? Yeah, it should. So we have a product of functions, f prime, or f and g. We want their derivative. Well, replace x with h, or replace x with x plus h. So replace all x's with x plus h, we get f of x plus h, g of x plus h. Minus, leave the x's alone. All over h. Now, how can we solve this? Well, we can't yet. What we need to do here is add a convenient zero. I made a mistake. That was not a good mistake either. That's not the derivative. Derivative is the limit. Can't go making that mistake. Derivative is the limit as h goes to 0 of that. Can't take that limit, but what we can do is add a nice 0. Which 0? Well, I want it to work out like that, so which 0 should I add? The other. No, I want the first one. Nah, whatever, that's fine. Now, notice here, these two middle terms are the same, but they differ by a sign. So that is technically adding a 0. Now what can we do? We can do some factoring. What kind of factoring can we do? These first two terms have an f of x plus h. These second two terms have a g of x.
Do we have to know this proof, or is this just clarification?
Excellent question. I will not ask this proof. So yes, I will not ask you this proof. And I get the feeling if I did ask a proof like this, it would just turn into, you know, you're having to memorize a lot of letters and numbers. But we did add a 0, and just like with when we multiplied by 1, just like with in some problems where we multiplied by 1, it caused the problem to simplify nicely. Adding this 0 allows for a nice factoring. And notice in this factoring, we have these two quantities in these square parentheses, which look kind of like derivatives. What can we do next? We can next split the fraction. Now this type of splitting of the fraction, we are going to see a couple times throughout the semester, where we take, so this fraction here has two things added together. This first large thing plus that second large thing. And we can split them over this h, meaning we can split the fraction by doing the first thing divided by h, and then the second thing divided by h. And right here, we can then take limits. As h goes to 0, that goes to f of x. This here, that limit is the derivative of g. As h goes to 0, g of x doesn't change. This fractional quantity goes to f prime. So now using the definition of the limit, or we can use the definition of the limit to prove the product rule by adding a 0, splitting a fraction, and then taking the limits. And notice here we do have the same formula, even though down here it's flipped around. The one function times the derivative of the other plus the derivative of the one times the other. Yes, I will not ask you this. This was for illustrating purposes. But any questions about that? The proof of the product rule is definitely more complicated than a proof of the sum rule, because in the sum rule, you don't have to add a strange 0. In the sum rule, you just have to rearrange and split a fraction like that. So I wanted to cover the product one rather than the sum one. But what's important to note is that we can't just take a derivative of a product like we took the limit of a product going piece by piece. We need to follow this product rule. So let's illustrate the product rule before going on to the 6th rule. Let's not. We don't have enough interesting functions to illustrate the product rule. Let's do a little bit more and then illustrate the product rule. Now, all we have so far, really, for those first 5 rules, we have derivatives of polynomials. And, well, they're, for illustrating product rule purposes, and less interesting than, like trait functions, exponential functions. So we'll illustrate the product rule in a few minutes. With the limit, we had that we could take the limit of a quotient piece by piece. With derivatives, we cannot take the limit of a quotient piece by piece, just like with the product rule. The derivative of a quotient, so f divided by g, where it's defined, meaning where the denominator is not 0. The derivative is given by this formula. So here up in the top, these are primes. Now, another reason to not write an exponent of 1 is because in calculus, 1 kind of looks a little like prime. But this in the bottom is a 2, an exponent of 2. The derivative of a quotient, f over g, is gf prime minus fg prime over g squared. Bottom function, derivative of the top function, minus top function, derivative of the bottom function, all over bottom squared. Let's look at an example where we illustrate this quotient rule. I'm not going to do 3x yet. I'm not going to do x to the first yet. Okay, let's illustrate the quotient rule with this function. A proof of the quotient rule, there is a way similar to the product rule where you add a convenient 0. We'll also cover a proof tomorrow with a result we cover tomorrow. Now, the proof tomorrow will take, maybe 2 minutes, whereas the proof with the definition would take maybe 8 or 9 minutes. But let's illustrate the quotient rule here. So here we have a quotient. We have x to the fourth plus 2x squared divided by 5x to the seventh minus x cubed. So we have a quotient. We have a top function. We have a bottom function. So we can find its derivative following the quotient rule. Quotient rule has 5 pieces. It has, now in describing quotient rule, I generally always say top function, bottom function, and then over here, bottom derivative top minus top derivative bottom over bottom squared. I think that's a lot easier to say than denominator, derivative, numerator. And denominator, numerator are really, really large words for quantities, which can easily be described with top and bottom. So the quotient rule tells us the first piece we need is the bottom function. There's the bottom function. The next thing we need is the derivative of the top function. I'm going to need more room. Do I have more room in that direction? First thing we need is the bottom function, 5x to the 7th minus x cubed. Times derivative of the top. What's the derivative of the top? Well, we can use our first 4 rules to find that derivative. The top is x to the 4th plus 2x squared. The sum and difference rule says we can take this derivative piece by piece. Derivative of x to the 4th, using the power rule with n equal to 4, is 4x cubed. The derivative of 2x squared, which is the next piece, well, remember, we can carry down the 2, just deal with the x squared, or the x squared. Derivative of x squared using power rule is 2x to the 1st. So we have 2 times 2x to the 1st, which is 4x. Any questions about those first 2 pieces? Bottom, derivative, top. Okay, next we need minus, then we need FG prime, top, derivative, bottom. So write the top function. Next we need derivative of the bottom function. Derivative of the bottom function, well again, it is a difference, but it's still 2 different quantities added together or subtracted together. So the sum and difference rule says we can take this derivative piece by piece. The third rule says we have a 5 there. Let's just look at the x to the 7th and then worry about the 5. X to the 7th, a power function. Derivative of a power function with n equals 7. 7x, 7 minus 1. 7 minus 1 is 6. So we have 7x to the 6th times a 5. Seven x to the 5th times a 5, or sorry, 7x to the 6th times 5. The 5 and the 7 make a 35. Any questions about the first piece of the derivative of the bottom? The next piece, the difference rule says carry that negative through. We have x cubed, derivative of x cubed using the power rule. N equal 3 is 3x squared. We did all that work, but we don't have the final answer because we didn't follow the quotient rule exactly. We still need divided by bottom squared. You don't have to square out the bottom, you can just leave it as bottom squared. But with this, it's definitely a good idea to take a step back and just look at everything that you did to make sure you follow the quotient rule. Bottom, okay, derivative of the top, 4x cubed. 2 times 2x, 4x cubed is 4x, minus the top times derivative of the bottom, 35x to the 6th minus 3x squared, all over bottom squared. And yes, you do not have to simplify. Simplifying that would not illustrate anything. Well, x's would cancel, but x's would have canceled in this step. So I left the x's here just for illustrating quotient rule purposes. Maybe I should have just put a constant along with it. But in your homework, I probably wrote don't simplify. Yeah, so in your homework for problem 2, I said don't simplify. Simplifying these, we will do some things where we simplify certain derivatives in order to examine the applications. And in those cases, the simplifications won't be, they won't be wastes of time, let's say. Simplifying this, distributing all that, illustrates on that. Any questions about illustrating the quotient rule? On the worksheet, I didn't say in the directions, do not simplify your answers, but don't bother simplifying your answers on the worksheet. So we have now 6 rules, 6 derivative laws. There are 10 more that we're going to look at. We haven't said anything about trig functions yet. Well, let's say something about trig functions. And in a condensed 6-week class, there are some things that you have to move around in the semester. With limits, there's actually something I am pushing off till next week. Now, why do I mention that? Well, I mention that because you need it to prove the derivative of sine. Let's start with 3. That's all I really have room for. So I'm not going to prove derivatives of these. I believe Jack in the workshop is proving, I don't know if he said both or just one, but I know he's proving sine. And to prove that, you do need a rule that we are actually going to cover in detail next Thursday, I believe it is. But let's just discuss the derivatives of the trig functions. Start with sine x. The derivative of sine of x is negative cosine of x. What am I doing? Sorry about that. I was getting way ahead of myself. Derivative of sine of x is just positive cosine of x. Sorry about that. That was a mental lapse. Derivative of sine of x is cosine x. The derivative of cosine x is negative sine of x. And proofs for both of those, you can use the definition. I won't cover directly those proofs. The derivative of tangent of x is secant squared of x. A proof for that is on the worksheet. Well, it will be, well, yeah, it is on the worksheet, number 4. You can prove this using the quotient rule, using these first 2, and using the sine squared plus cosine squared equals 1 identity. There are also rules for the other 3 trig functions, which I'll mention in a moment. But first, let's just illustrate 1 or 2 of these. Find f prime of x, f of x equals let's do 4 cosine of x right now. Yeah, let's just do 4 cosine of x. So we'll illustrate, in this case, the second of these trig rules. F prime of x. Well, we have 4 cosine x. The first thing we do is notice that there's a 4 in front. The third rule says if you want the derivative, you can look past that 4, provided that you remember to write that 4. So the derivative here, bring the 4 down, and then deal with the cosine x. Derivative of cosine x is negative sine of x. So we have 4 times negative sine of x, and if I ever ask you a question, find a derivative, on a homework or a test, it will say don't simplify. So you could technically leave your answer in that 4 times negative sine x, but with a simplification like that, that's I will always do that. But well, whatever you want for that. Any questions about that one? What if I change this function? And said 4 cosine x plus 7. What's the derivative of that? Well, the sum and difference rule says we could do it piece by piece. Derivative of 7 is 0. So it's the same derivative. And the same if I made that a negative 7. Derivative of negative 7 is still a constant. Derivative of that is 0. We have the other 3 trig functions. Cosecant x, secant x, cotangent x. Derivative of cosecant x. So on the worksheet, number 4 says to prove the derivative rule for tangent x using the quotient rule. Similar proofs follow for these other 3 using a quotient rule, writing them in their fractional forms with sine and cosine. I'm not going to cover those proofs. We will use them. We will use these rules. Derivative of cosecant x is negative cosecant x cotangent x. Derivative of secant x is positive secant x times tangent x. Derivative of cotangent x is negative cosecant squared of x. And again, proofs of those 3 do follow from quotient rule. Now, toward the end of next Thursday, I may go through some details of the derivative of sine of x, but not right now. So we have now 12 derivatives in our list of derivatives. There are 4 more we're going to cover. Derivatives of logarithms and exponential functions. Now let's just start with these 2. Let's start with the natural exponential. The derivative of e to the x is itself. Derivative of e to the x is itself. E to the x, a very important function in math, physics, chemistry. One of the reasons it's so important is because it gives the slope of the tangent line at any point, meaning its derivative is itself. More on that in a moment. Derivative of the natural logarithm of x is 1 divided by that x. So we have here the natural exponential function and derivative. Well, what about the general exponential function and derivative? Well, I'll give you a moment to write that down because I'm about to erase it. What about the general exponential and general logarithm? Meaning, what about b to the x, where b isn't the natural exponent, or it could be actually. And the general logarithm, logarithm of x, general base b. Well, they're similar to the natural rules, but instead of the derivative of the general exponential being itself, it differs by a constant. B to the x times the natural log of b, the base, natural log of b. And here we also multiply by the natural log of b, but we multiply in the denominator. Meaning we divide. So the general exponential, of course, if you let b equal e, these do give you the two previous rules because the natural log of b is 1. But the general exponential derivative has an extra constant versus the natural exponential. So let's illustrate the way to prove those 4 rules. You start with the general exponential. You use that to prove the natural exponential, and you use a result from next week to prove the rest. So I'll just write here proof of exponential, and I'll say here the natural exponential, even though it looks like we're using the general exponential. Now, what does that mean? Well, let's see what that means. Derivative of an exponential function looks like that. Limit as h goes to 0, f of x plus h minus f of x all over h. So here we have b to the x plus h minus b to the x all over h. What can we do with this? Well, what we can do is not go to that line. What we can do is use our exponent rules. B to the x plus h, b to the x, b to the h. So all we did in that first observation is use the natural, or use the exponential rule. You know, if you have b to the x here, b to the h here, all together, you have x plus h copies of b. Well, what can we do with that? Both terms in the numerator have a b to the x. Earlier in this semester, I probably said when we were discussing exponentials that we will see a couple times why the natural exponential is nicer, at least in calculus, and because of that, other branches of science. One of the reasons is illustrated in that chart where the derivative is itself. But in this proof, we will see why the derivative of the natural exponential is itself. Factor out a b to the x. Now, what can we do here? We can actually pull b to the x out because this limit is as h is changing. B to the x doesn't have any h's. B to the x times that. Now, what just happened there? Well, what happened there is we've shown what the derivative of a general exponential is. B to the x times this limit. This limit can be rewritten. Because 1 is b to the 0. Why does this matter? Well, we saw when we first discussed derivatives on Thursday, we saw what looked like two definitions of the derivative. This right here uses the first. The first one gave us the derivative at a point. And the reason that the natural exponential has derivative itself is because by definition there is an exponential for which this slope of the tangent line equals 1. So the natural exponential is defined to be that exponential. So of all exponentials, there's exactly one where the slope of that tangent line equals 1. I should draw that a little more in detail over here. The natural exponential is defined to give it. So I'll finish the sentence and then illustrate it with the graph. The natural exponential is defined so that the slope of this line is 1. And this line is going to refer to a graph that I won't be able to fit underneath it. So I'll draw the graph in more detail over here. Remember, we discussed the graph of an exponential function, a general exponential function. It goes through the point 0, 1. So what does the this in that sentence refer to? Well, remember, exponential functions always go through the point 0, 1. Now with a larger base, it becomes more slanted upward and it goes down a little faster. But of all of those, there's exactly one where the slope of that line equals 1. So that this refers to this line. The natural exponential is the one where that slope is exactly 1. Because of that, for the natural exponential, this limit is 1. So in case you were wondering why the natural exponential is more important, one of the reasons is its derivative is itself. One of the reasons is by choice. We choose the natural exponential so that this limit simplifies nicely. But why do we want that limit to simplify nicely? Well, because that choice exists. There is one of them where the slope of that line is 1. Let's call it the natural exponential. And it happens to be very useful in math and physics and chemistry and probably other branches, but it definitely shows up in lots of science, let's just say. So yes, I will not ask you to prove that. But in case you were wondering, we just saw two different reasons that the natural exponential is more convenient. Any questions about that? Okay, so let's, we have that list of 16 rules now. Let's use a few of them. So for the next 15 minutes, at the end, I am going to introduce one other topic. you know, it's a quick topic. But for the next, say, 7-8 minutes, let's do a couple examples where we use these. What do I write down? Oh, and I will post that list of derivatives on Canvas once I scan them. Example, find f prime of x 1 or a. Let's see, we didn't illustrate product rule. Let's do this one first. Let's really drive power rule in. X to the 7th plus 4x to the 3rd. No, I already did one like that. Plus 4x plus 3x, no, plus x to the negative 5. Let's throw a negative exponent on there. B. F of x equals we didn't do an exponent, let's do an exponential. E to the x plus x. Let's throw some negatives in here. Well, let's do a product next. X equals x cosine, no, let's do sine first. X sine of x, we did cosine. Let's start with these three and then we'll do a couple more. So there will probably wind up being, my guess is we'll do 5 right now. So let's start with the first one. Well, we have 3 things added together. We can do the derivative one piece at a time. Oh, I didn't throw any negatives. Yeah, that's okay. We'll put negatives in the next one. X to the 7th, derivative of that, use the power rule, you get 7x to the 6th. Plus 4x. How about 4x? How do we handle 4x? Well, let's write the 4 first, and then worry about the x. What is x? Side word. X is x to the 1st. So it is a power function. X to some number. So we can use the power rule, the second rule in our list. Power rule says the derivative is the exponent, which is 1 times x to the 1 minus 1. What does that equal? It equals 1 times x to the 0. Equals 1. So using the power rule, we see the derivative of x to the 1st is just 1. So the derivative of 4 times x is 4 times that 1. I'll write it like this for this example. I'll write it as 4 times 1 for this example. Next, we have x to the negative 5th. Derivative using the power rule. Exponent is negative 5. So power rule, bring the exponent down, times x. So the negative 5 minus 1. We're always subtracting 1 from our exponents, which makes that an exponent of negative 6. So, you know, positive exponents definitely will show up much more frequently. And it's very, now when you do these, when you practice these a lot, certain things become instinct. Now, unlike the first one, notice we went from exponent 7 to exponent 6. So instinctively, it might feel like you should go from exponent negative 5 to negative 4. But we are, using the power rule, we are subtracting 1. And because of that, the negative exponent gets subtracted 1. It goes farther from 0. It goes to negative 6 in this case. And just not writing 4 times 1. We have just changing that to a 4. But do observe in this example, this is the first time we've seen this, the derivative of a constant times x is just that constant, and it follows from the power rule. So when doing that, it's very, it takes a good amount of time to do the power rule with an x to the first, but it will always work out. The derivative of a constant times a function is just that constant. And that's going to show up a lot throughout the semester. Any questions about part A? Part B, f of x equals e to the x plus x. Well, again, we have 2 things added together. We can do the derivative one piece at a time. Derivative of e to the x, following rule 13 in our list. Derivative of e to the x is itself, e to the x. What about derivative of x? Well, x is 1 times x. Derivative of a constant times x, using the power rule, is just that constant. So we have e to the x plus 1. Any questions about that? What was that, the second one? I will mention, if that were a negative x, how would that change this answer? Well, derivative of negative x, negative 1 times x, constant in front of x is negative 1. So we'll make that a negative. Okay, let's do part C. I'm actually going to change this a little. I'm going to make it x to the 5th. Yeah, 5 is a good number. X to the 5th sine of x. I think that'll illustrate the product rule a little better than if I left it as x. X to the 5th sine x. Well, this is our first product. We have something with x's times something else with x's. How can we take that derivative? Well, the product rule says we can't just do it one piece at a time. We need to follow the product rule, which says the derivative is derivative of the first times the second, plus the first times derivative of the second. What's the derivative of the first? Power rule, derivative of x to the 5th. 5x to the 4th times the second. Just like in quotient rule, you just rewrite the one piece when you have to rewrite it. Plus, so right here we took the derivative of the first, left the second, plus the first, which is x to the 5th, times derivative of the second. Derivative of sine, rule 7 in our list, derivative of sine is cosine. And you don't have to bother factoring out an x to the 4. But here we have the product rule. Derivative of the first times the second plus the first times the derivative of the second. Any questions about part C? Okay, let's do another 2 examples. Let's see where that leaves us. So we did that exponential, we did a product, we did that. It's very important to practice these. Part D. Let's see, we haven't done one like that. X 3 to the x, another product. Oh, we did sine. Let's do tangent. Let's do these two things. So again, for this first one, we have a product. We have x and 3 to the x, and they're multiplied, so we need the product rule. So that's the derivative is derivative of one times the other plus the one, derivative of the other. Derivative of x, well, x is just 1 times x. Derivative of constant times x, using the power rule, is just that constant. So we have 1, derivative of the first, times the second, 1 times 3 to the x, plus the first times the derivative of the second. Derivative of 3 to the x using rule, the second to last rule, so rule 15. Derivative of 3 to the x, well, it's an exponential function with base 3. Derivative of exponential function is b to the x log b. So derivative of 3 to the x is 3 to the x log 3. And writing 1 times kind of gets in the way. So I'm not going to write it as 1 times. I'm just going to write it like that. But we do have our 4 pieces of the product rule. First, derivative of the second, derivative of the first times the second plus the first times the derivative of the second. And with product and quotient rule, I always like looking back at my work and just observing that the 4 pieces for product rule, the 5 pieces for quotient rule, I like observing that they are there. Part E. Well, any questions about part D? So part E, we have a quotient. So we'll need the quotient rule. Bottom, derivative top, minus top, derivative bottom, over bottom squared. Yeah, don't worry about simplifying. This step in simplification is not writing the 1. That's, it's not necessary, but it's recommended. Simplifying a quotient rule is not recommended unless you have to. But we have bottom, so let's write bottom. Times derivative of the top. Top is something plus something else. The derivative is the derivative of the one thing plus derivative of the other thing. Derivative of tangent, using rule 9, secant squared of x. So in discussing the trig rules, I frequently don't mention the x. And derivative of tangent of x is secant squared of x. But I'm not sure that I would recommend thinking that exact set of words while going through them. It's much fewer words to think. Derivative of tangent is secant squared. Derivative of 1 is a constant, derivative is 0. Minus the top times the derivative of the bottom, which will fit here, I think. Derivative of the bottom, well, again, we have 2 pieces added together. Derivative of cotangent, using rule 12, I think it is. Negative cosecant squared of x. Derivative of x, just like up here, 1 times x, derivative of 1 times x is that 1. All over bottom squared. And you don't have to simplify this. You have much better things to do than simplify fractional. So these, well, any questions about that last one? Okay, I guess we'll do that small thing I thought we would have time for. We'll do that at the beginning of tomorrow. But definitely, today more than any other day for these 6 weeks, it's a good idea to practice problems like number 3 on the worksheet before our class tomorrow. Because what we're going to do tomorrow assumes at least a little comfort with some general structures. And that comfort comes from working on some problems like these. Every time you work on these, you get a little more used to the rules. So do practice problems like problem 3 before tomorrow. Part I looks a lot like this one. Oh, I should also mention the power rule. We didn't do any with non-whole number exponents. So like in part C, you have x to the 9/2. It would be 9/2 x to the 7/2 following the product rule, or following the power rule. So any questions? I will post solutions to the exam shortly.